Jai Hind to all of you. I am Dr. Gaurav Saxena, Associate Professor in EC Department. So today I have discussed very complex topic which is associated with antenna and wave propagation KEC 603, which one is Yagi antenna and folded dipole antenna. So these two topics which are very useful for UT exam for EC third years 6th semester students. So what is the meaning of Yagi Uda? Yagi and Uda is the two Japanese scientists which invented this antenna, which is used for very high frequency, ultra high frequency in the span of 30 megahertz to 3 gigahertz. And we have to be use this antenna for VHF and UHF band. So VHF, that means the very high frequency, and the UHF is the ultra high frequency. So what is the salient feature of Yagi Uda antenna? So Yagi Uda antenna having a salient features which I discussed to you. First one is the salient feature is high gain antenna. So this Yagi Uda antenna introduce a high gain because this antenna works as a end fire array. So that means what is the meaning of end fire array? The radiation pattern of that particular antenna in the antenna array axis. So we can say this type of antenna is called a also a end fire array. So end fire array properties having a high directivity, low half power beamwidths and low BWFN. So they provide a high gain approximate 10 dB to 20 dB. So this type of gain is to be varied from 10 to 20 dB by using the how many number of directors you have to be used in that particular Yagi antenna. So this is the diagram of Yagi Uda antenna. So this one is reflector, this is the reflector, we have to be known as that is reflector. This is folded dipole antenna and this is the directors. So in this type of antenna, there are two types of antenna element we have to be used. First one is active element, second one is passive element. Active element, that means we have to be introduce a inputs in that particular circuit or in that particular dipole. So we can say this is a active element because we have to be giving a input signal or we receive a signal by in a driving element, or we can say folded dipole element. So this is the active element, this is a passive element. Reflector also a passive element because we does not provide any input or we can take any output from that particular element. So we can say this is a passive element, and directors also a passive element. So the front view of that particular antenna we have to be represented here. This is the reflector. So this is the driving element, or we can say folded dipole antenna, and this is the directors. So in the if we design any Yagi Uda antenna, so what is the length of reflector, what is the spacing between the reflector to driving element, and what is the spacing of driving element to the directors, we have to be calculated, and what is the length of this first director, second director, third director, fourth director and fifth director. The radiation pattern of this direction is unidirectional antenna, or we can say this is a unidirectional antenna where directivity or half power beamwidth is to be maximized in the direction of antenna array axis. So this is the antenna array axis. So we can say this type of antenna is also called a end fire array antenna. So we have to be discuss here how we design this antenna and what is the application of this antenna. So first the property of this antenna is high gain. So this type of antenna is provided a high gain 10 dBi to the 20 dBi. So dBi, that means the gain with respect to the isotropic antenna. So we can say this is a dBi. So 10 dBi to 20 dBi. or you also calculate the gain with respect to the dipole antenna, or we can say dBd. So we enhance the gain from 2.16 dB with respect to that particular antenna. So you also calculate this type of antenna gain of any antenna with respect to the dipole antenna. So second one is high front to back ratio. So what is the meaning of front to back ratio? So front to back ratio is the ratio of directive power to the opposite power. If I can say, this is the radiation pattern of any Yagi antenna having a power is 110 milliwatt in forward direction and 1 milliwatt in reverse direction. So what is the front to back ratio? So front to back ratio is the ratio of forward power 10 milliwatt to the 1 milliwatt, or we can say this is the front to back ratio is 10. So in this type of antenna, the front to back ratio is very high, in the range of 30 to 40. So that means 30 to 40 times forward power is more than the reverse power. So we can say the high FBR they provided. And third one is high directivity and high gain, and third one is the front to back ratio is to be high, and bandwidth BWFN and half power beamwidth HPPW is very small with respect to the others. So we can say the directivity is high, but the beamwidth of first null and the half power beamwidth is very small for in this case. And the fourth one is bandwidth is very high. So what is the meaning of this? The antenna works in a particular bandwidth. So that means this type of antenna or Yagi antenna radiates electromagnetic energy in a wide band. So we can say this type of antenna having a high bandwidth. So fifth one is used as a end fire array. किसकी तरह यूज करते हैं? We have to be use this as a end fire array. So that means what is the meaning of end fire array? Two types of array we have to be study here. First one is the broadside array and end side array. So in the broadside array, if we placed a similar antenna in, with respect to the having a equal space with respect to the others, if the radiation intensity maximum to the antenna array axis, or we can say 90 degree or 270 degree, so we can say this type of array is called the broadside array. But in this case, if the antenna is to be radiate, or we can say it is a highly directive antenna with respect to the antenna array axis, then that means if your antenna radiates in the direction of antenna array axis, so this is the antenna array axis, so they radiates in the direction of antenna array axis. So we can say this type of antenna works as a end fire array. So we can say how we calculate the end fire array elements, and how we calculate the directivity, how we calculate the beamwidth of first null, how we calculate the half power beamwidth, which is in the case of Yagi antenna. So this is the feature, salient features of Yagi antenna. Dipole element is usually folded dipole. We can say why we use this type of driving element having a folded dipole. How we not use this single dipole antenna? Because if we fed this to the receiver of TV, this is the TV receiver, so how much energy is to be received by this folded dipole antenna? So that means this cable having a impedance of 300 ohm, in the range of 300 ohm, but the folded dipole antenna having a single folded dipole antenna, or we can say single half wave dipole antenna having a input impedance is 73 ohm, or we can say radiation resistance is 73 ohm. So we cannot receive the maximum power, because the maximum power states that the powers to be stimulated or radiated when the load resistance is to be equal to the input impedance of the source. So if this input impedance or radiation resistance is 73 ohm for single dipole antenna, and the characteristic impedance of this line is 300 ohm, so we cannot assume that the maximum power is to be received by this TV receiver. So we can say, so how we improve the radiation resistance of folded dipole antenna? So we use the folded dipole antenna to increase the radiation resistance for n is equal to 2. So double folded dipole antenna having a radiation resistance, we have to be calculated by n square ZD, where ZD is the dipole antenna impedance. So we know that the dipole antenna impedance is 73 ohm, and the two folded dipole antenna n is equal to 2. So 2 square is 4. So we can say this is 292 ohm, which is highly comparable to the 300 ohm. So we can say, so we use a folded dipole antenna rather than a single dipole antenna. So the input impedance is 300 ohm, or we can say 292 ohm, which is likely comparable to the 300 ohm. So we can say this receives the maximum power, and this power is to be received by that TV receiver. So that means maximum power is to be received by TV receiver. So we can use these folded dipole antenna. So what is the parameters we have to be calculated in folded? If we design a Yagi antenna, so the reflector length, so what is the active and passive element? The most important, the active element is folded dipole antenna length, and what is the spacing between the other elements. So if I can say the reflector length is 152 by f in meter, but if you find the reflector length LF in foot, so we use the 492 upon f in megahertz. This one is this feet. So if you calculate the length in feet, so we use the formula for calculating the reflector length, or we can say this is the reflector length, which one is 492 upon f, where you put the f in megahertz. So they giving a answer directly in the feet. So the what is the driven element length? So driven element length in meter we have to be calculated by 143 by f. But in this case, if you want a driven element length, or we can say folded dipole length in feet, so we can say this one is 475 upon f, 475 upon f in megahertz in feet. And what is the first director length? First director length in meter we have to be calculated 137 upon f. But if we calculate in feet, so what is the first driven element or first director length, which one is 455 upon f megahertz, itne feet. So we easily calculate, if I can say we design a 3 element Yagi antenna for 500 megahertz frequency. So you directly put the 500 megahertz. So that means 500 you have to be put it, 492 is put it. So we easily calculate what is the reflector length in feet. Or if you want this formula for meter, so we use the 152 by f. So, and what is the spacing? Spacing between the directors is 0.13 lambda. Spacing between the director and dipole is 0.13 lambda. Spacing between the reflector and dipole is 0.25 lambda. And the length of successive director reduced by 2.5 to 5%. So by using these formula or these relation between the reflector length and spacing at particular frequency which have to be designed that particular Yagi antenna, we easily calculate it. So, first example we have to be taken. So, if I can say we design a Yagi antenna for 500 megahertz frequency, or we can say what is, you design a 3 element Yagi antenna for 500 megahertz frequency. So, what is the 3 elements? 3 elements, first is reflector, which is, second one is folded dipole, third one is director. So, in this question we summarize that, or we can say 3 element Yagi antenna you have to be designed at 500 megahertz frequency. So, what are the 3 elements? So, we design a Yagi antenna having a, what is the reflector length and the spacing between the reflector to the folded dipole. And what is the length of the folded dipole antenna? Folded dipole antenna. And what is the distance between the folded dipole to the director? And what is the director length? And the between folded dipole and the director length, we have to be distance we already calculated. So, by using the formula, what is the reflector length, how we calculate it? The reflector length formula is 492 upon f megahertz. How much feet? So, 492 upon, directly we have to be put 500, because in that particular formula we have to be put the frequency in megahertz. So, 500 megahertz is here. So, we easily calculate what is the reflector length is 492 upon 500 feet. And second one is what is the folded dipole length. So, the folded dipole length is 475 upon f megahertz. So, that means 475 upon 500 megahertz. So, we put the frequency in megahertz. So, this one is this feet. So, and what is the first director length? So, length of director first, which one is 455 upon f megahertz. So, we easily calculate the what is the length of first directors. So, we easily calculate what is the reflector length, what is the folded dipole length, and what is the first director length. Then we calculate the what is the distance between the D reflector to the folded dipole. So, which one is given by 0.23 lambda. So, we easily calculate lambda is equal to C by F. What is the formula? Lambda is equal to C by F. C is equal to 3 into 10 is power 8 upon F is 500 megahertz. So, we easily calculate the lambda in meter, and we put the value of lambda in meter here. Then we calculate the length between the reflector and the folded dipole, which one is how much meter, and we convert it into the feet, because all the length we have to be calculated in feet. So, 1 meter is equal to 3.06 feet. So, we easily calculate how much the length between the, what is the distance between the reflector and the folded dipole, and how we calculate the distance between the folded dipole and the first director, which one is 0.15 lambda and 0.15, and you put the value of lambda in meter by using this formula C by F, and you put it Then we calculate the distance between the first dipole antenna to the folded dipole to the first directors. We easily calculate and we convert it into the feet by using the formula 1 meter is equal to 3.06 feet. Then we design a Yagi antenna for 500 megahertz frequency. So how we calculate it? So this one is reflector, this is folded dipole, this is direct. So the distance between them we easily calculate, or we can say this is the reflector length, L reflector, we easily calculate it. This is the L folded dipole length, L folded dipole, and this is the length of first director, we easily calculate it, and the spacing between the first reflector to the dipole we also calculated, which is 0.23 lambda, and the distance between the first dipole or to the first director, which one is 0.15 lambda, we easily calculate it. We calculate the lambda in meter and we convert it into the feet, and we also calculate the length of reflector in feet by using the formula 492 upon f. We put it, suppose this one is 1.2 feet, or this one is 0.92 feet, this one is 0.86 feet. So you mention it, what is the length, and you also mention the what is the spacing, or we can say 0.12 feet, this one is 0.08 feet. So you put it and you design a Yagi antenna for 3 element having a frequency, resonant frequency is 500 megahertz. This is the radiation pattern. So this is the polar pattern of the Yagi antenna. So we can see that this is the unidirectional antenna. So that means, what is the meaning of unidirectional? That means they reflect or they receive or transmit the signal in a particular direction. And this is the major lobe. This is also called a major lobe. So major lobe is unidirectional. So that means Yagi antenna also a unidirectional antenna having a back lobes. You can see that this is the back lobe, or we can say this is also a minor lobe. This is minor lobe, and this is back lobe. We also mentioned that Yagi antenna having a high front to back ratio. That means the major lobe intensity if we measure and the back lobe intensity if we measure, so the ratio of this is to be high in Yagi antenna. So this is very useful for TV reception and use where the single frequency application is need. So this is the application of Yagi antenna. So we easily discuss Yagi antennas, but in the modern days this Yagi antenna is to be modified. This is circularly polarized Yagi antenna. So we use a helix structure. So driving element is to be used as a helix structure to provide a circular polarization. So what is the meaning of polarization? Polarization is the locus of electric field vector with respect to the antenna. So we can say this is polarization. If I can say the two vectors which are perpendicular to each other, if we transmit a electromagnetic wave having a two vectors which are perpendicular to each other and having a same amplitude, so we can say E1 is the same amplitude and this is perpendicular to each other. So the locus of that particular vector is circular. So we can say this type of wave is called a circularly polarized wave, and we use this Yagi antenna having a circularly polarized when we use a driven element as a helix structure. So by using the circular polarization, we also calculate the what is the axial ratio. So axial ratio is the ratio of maximum electric field mod upon minimum electric field mod for, in this case, if E1 and E2, two vectors which are perpendicular to each other and having a equal amplitude. So in this case, E max is equal to the E mean. So this one is E naught upon E naught. So this is 1. So that means the axial ratio of circularly polarized antenna is 1 in the, but in the dB, if we calculate in the dB, 20 log base 10 into 1, so log 1 is 0. So in this case, if I can say कि some antenna or this Yagi antenna having a axial ratio is 1, or we can say circularly polarized antenna. So in this case, the axial ratio of that particular antenna is to be 0 dB. So by using this drive-in helix structure, we modified the Yagi antenna for vehicular application as well as the mobile application for having a axial ratio is 0 dB, or we can say circularly polarized antenna. Thank you.